What's a log-canonical bracket? Just put it on the board. It's a very familiar object. So log-canonical Poisson bracket. Let me work over complex numbers. So on Cn is the Poisson bracket of this form. So the right-hand side, when you evaluate it at coordinates, the right-hand side is just product of xi and j and some constant. So for the little comment that for every symmetric matrix of lambda ij, for me this is just numbers. This Poisson this bracket is actually Poisson, so it's integrable. It's kind of a tautological comment, but the statement is that this satisfies Jacobi identity automatically. And the idea to discuss today goal is to describe Poisson deformations of a log-canonical bracket of this form. Meaning that I want to deform the right-hand side of this bracket slightly. And the question is, how can I do it in such a way that the Jacobi identity is still preserved for the deformed expression? I worked on this problem for a while, and a few years ago, the result with the Brent Payment Travis Shadler, which we call the local Torelli theorem for log symplectic manifolds. And that theorem in particular was implying the answer to these questions, to the question that to this goal.
You mean algebraic deformations, right? In the class of algebraic Poisson brackets.
Analytic is fine. But this theorem applied for the case. There was an important condition that I needed to close. It was applied applicable for the case when the matrix of the coefficient has a non-zero determinant, a particular even size has maximal rank. So under this condition, that the bracket is also called log symplectic, log canonical. So we had a general statement which was providing a solution to this goal. And I'll state the theorem. I'll state some case of the theorem that we need later, but I want to focus today on more general case when this the non-degeneracy condition is not satisfied, but it can be corrected using some torus action. So today I'm going to assume that there is also, in addition to the Poisson bracket, there is algebraic torus acting on Cn. There is some torus of some rank, which rank doesn't have to be equal to n, can be anything. And assume it acts on Cn in such a way that each coordinate is a weight vector. with respect to this action. What does this mean? That if I denote by T sub R, T sub maybe T sub K, be element of this torus that has only one non-trivial coordinate at K spot. So the action of the torus has to be of the form that Tk acts on the coordinate xj by rescaling to some power kj or beta kj is an integer. So every coordinate just gets rescaled by certain amount.
So
Uh,
what is R?
R can be any number, typically less than n, but can be even bigger than n if you want. So it's not equal to n. So you see, in particular, this action preserves the Poisson bracket, because when you rescale one of the coordinates on both sides, the scalars cancel out. So this bracket is T invariant. And when I deform the bracket, I want to preserve this T invariance. So the goal for today, sort of more specific version of that goal, describe T invariant for some deformations. Log-canonical Poisson bracket. I want to impose some non-degeneracy condition which would replace this one. So in general, trying to describe all Poisson deformations of bracket without any assumption is sort of hopeless, because I mean I could also start with zero Poisson bracket and try to describe Poisson deformations of zero Poisson bracket, and that's sort of meaningless task. More or less, I want to replace some. I want to impose some non-degeneracy condition, and how the condition that seems to work is having open T-leaf. Open T-leaf. So a T-leaf is a union of some translations of a symplectic leaf. I'm assuming that there is a symplectic leaf whose translation, union of all translations form an open subset. So numerically, you can check this condition using the matrices lambda and matrix of this beta by requiring that they combined have full rank. Matrix, the n plus r times n matrix goes from lambdas followed by betas has to have rank, maximal possible rank n. So that's the standing assumption, and I want to describe some deformations of this log-canonical bracket that preserve T invariance. Any questions so far? Okay, so I'll start describing deformations by talking about first order deformations and then upgrading them to honest deformation, actual deformations. So the first order deformations usually they have theory that govern them. In this case, it's Poisson cohomology. First order deformations. They're given by second Poisson cohomology. And moreover, I'm only interested in key invariant deformation. So I take key invariant part of the second Poisson cohomology. So if you have seen second Poisson cohomology before, then that's good. If not, then just think of this as first order deformations. So I'm gonna now use the action of this n-dimensional torus that acts on C to the n by rescaling. And I'm gonna decompose this second Poisson cohomology into its weight components. The thing here is W weight. Component with respect to the torus to start to the end acting on C to the n.
But it's R. Used to be it start with the R.
Yeah, it used to be C star to the R. So there are two tori in question. So there is this T, which is used to start to the R. And here I'm also using the action of this torus as well. And if I want to, I only want to take to look at the T invariant part. So here I'm imposing T invariants, which can be expressed in terms of this coefficients beta in this form. So this means that this weight is T invariant. Okay, so I want to describe for you which weights contribute to this. So because for most of the weights, it will happen that this component is just zero. So let me now describe which components contribute to this decomposition. Couple easy statements. So one easy statement that zero does contribute always. Yeah, let me X here is always zero. So the zero component was contribute and it has dimension in choose two. That's easy part. So that component corresponds to deforming the coefficients of lambda ij. So you can n choose two independent coefficients lambda ij. You can deform them independently however you like. Those are the first order deformations that I'm talking about here.
So, sorry, just here, when you're saying these are the first order deformations, are these not the ones of the rank condition? These can be.
Can you say it again?
Preserve the rank of lambda is what you're saying.
No, they don't.
They don't preserve the lambda, but whether they preserve this rank.
Oh yeah, this is open condition. Yeah, I forgot to say that this is open condition. So small deformation will preserve this. Okay, so now, however, for every, so this zero component sort of has big dimension. However, the other statement is that for every non-zero weight, and I'm always talking about T invariant weights, the dimension And this component is always 0 or 1. All other wave components, if they contribute at most one-dimensional summand, and if this component is non-trivial, then W has to be of special form. W necessarily has to be of the form where most of the components are non-negative except precisely two entries which are -1. That's a part of the statement of the lemma, that there are precisely two indices I and J where W attains -1 and the rest are non-negative integers.
Which means that you can add constant bracket. Like xi bracket with xj is lambda.
Sometimes, yeah. So if all of these are 0 except 2 - 1, then you would be adding constant.
Could you please clarify what do you mean by deformation? You know, that would be
So here I'm talking so far about first order deformation. So I would be adding here to the right hand side, I would be adding epsilon times something.
something what? It's a polynomial in X or what?
Yes, polynomial. First order deformation would be polynomial. So epsilon times some polynomial, and the requirement is that that bracket satisfies Jacobi up to epsilon squared terms.
Up to epsilon square. So it will not be a Poisson, true Poisson bracket. It will.
It's
Not yet. So here is just first order deformations, and then true Poisson bracket would mean that it satisfies on the nose, and Jacobi identity on the nose. Right. Okay, but so and then we also have more information about what kind of IJs can appear here. So the third part of the lemma right here. So the third part of the lemma, we construct a graph using the following rule. So the graph will have n vertices, and the edges will reflect appearance of this weight of this kind. So we add an edge I connecting to J each time whenever there is a W that contributes to the Poisson cohomology and that has -1s that coordinates I and J. So every time we have contribution to Poisson cohomology, disregard 0 ones, just look at the other non-zero weight contributions. We add an edge connecting I and J whenever that appears. And then there is the statement about this graph. First of all, doesn't have, it has no multiple edges. Meaning for every pair IJs, there is at most one weight of this form that contributes to the Poisson cohomology. And second statement, it also has no vertices of valency 3 or higher. The graph basically is just union of chains, cycles, and isolated vertices.
Here a picture for n equals 2.
For n equals 2,
So then either the branch is full rank or it's 0.
yeah, it's either full rank or 0. So
It's a graph. A graph look.
the graph would be like 1 and 2 either connected by an edge or not, depending whether Poisson cohomology contributes, whether there is weight of the form -1, there are no other entries here, whether there is a weight or not that contributes to this. And I think the answer is basically if lambda is equal to, I think, yeah, in this case, there is always an edge connecting 1 and 2. Because in dimension 2, integrability is automatic. So that's a very simple picture. So when you have 3 vertices, the pictures could be different. So there are always there are possibilities for when there is only one edge. There could be 2 edges, and there's some examples there are even 3 edges. So that's also possible. Now, when you pass to 4, then you cannot have 6 edges because then this valency condition would be violated. So you have at most 4 edges in when n equals 4. Part of the statement, by the way, is that the first order deformations are finite dimensional, so that's not non-trivial. Certainly, if that open T-leaf condition is violated, then the second Poisson cohomology can be infinite dimensional. So always finite dimensional in degree 2. So meaning first order deformations are finite dimensional, and moreover, they satisfy this nice structure. So those are first order deformations. Now the question is like when you add them, the next question is when you add these first order deformations to Poisson bracket, whether the Poisson bracket can be made Poisson on the nose, not only up to epsilon squared terms. So if you have a situation when the weight contributes, then well, there is up to constant unique bivector that has this weight. So you can cook up a unique bivector, and that the bivector that contributes to the Poisson cohomology. So actually, if you just look at one edge, then phi 0 plus lambda plus, let's say, epsilon times rho w is honest Poisson deformation, where phi 0 is my log-canonical bivector. Here's lambda ij xi xj. So when I'm only talking about one edge, then the first order deformation is actually honest Poisson deformation, so I don't need any epsilon squared term. So that's some easy exercise. But the non-trivial statement, non-trivial thing to consider is when we have several edges and we are adding all the first order Poisson deformations, then it will not be Poisson on the nose. Such a deformation is not Poisson on the nose, but it can be fixed by the way of the following statement. This is main result. So for the case when torus is just a point, it's that local Torel theorem that I was mentioning before, that's joined with Prim and Schedler. The statement is as follows. So assumption, the standing assumption we have a log-canonical bracket. Has open p-leaf. One more assumption that we hope to get rid of, but we need to use it in the current version of the proof. So let the graph I constructed over there have no cycles. Then every first order deformation that entirely sits in the components which are not zero. Is unobstructed. What does unobstructed mean? So in other words, there exist power series that starts with log canonical bivector and whose linear term is the one you fixed. And then it also has higher order terms. And this power series is Poisson. And also T invariant. Pi zero is the log canonical.
Such a power series essentially unique for a given pi one.
It's essentially unique up to change of variables that might involve epsilon as well.
Yeah.
We don't have a proof that this converges always. So in principle, it could be formal power series. But in a lot of cases, it actually stops at some point. So it's algebraic in many applications, but sometimes it's not algebraic. In all examples, it converges so far, but we don't have a proof that it converges.
And in the case of cycles, is this false or just not proved?
In the case of cycles, for the case when torus is trivial, we have a proof. When the torus is not, when torus is non-trivial, we suspect it's true, we don't have a proof. But the proof in the case of cycles for trivial torus, actually much more complicated than the case without cycles. So without cycles, this theorem actually we found elementary proof now, but initial proof that also covered cycle case that was very technical, involved infinity algebras. So the hope is that it should be true with cycles as well.
Could you repeat once again? So if torus is trivial, so then what does this mean? So this condition,
Then open T-leaf just means having open symplectic leaf.
but then the conclusion of the theorem.
Well, the same conclusion. So, except that this part is sort of irrelevant now. So the conclusion is that then your assumption is that you have log-canonical bracket, which is also log-symplectic, so has maximal rank generically. In that case, you don't need no cycle assumption even.
So just. Yeah,
And the statement is that any first order deformation that lies in non-zero weights entirely is unobstructed in this sense.
weight. My understanding was that weight is related to.
Right. So the weight here refers to the torus C star to the n, not to the T weight. Here I'm talking about when I say weight, I mean weight of C star to the n. And I impose this condition to say that it lies in zero T weight. It corresponds to T invariant part.
Right. Can I ask about the role of the torus in the degenerate case? Because so you make the rank, you make it full rank when you add the beta k or whatever. That means that they must span the kernel of the lambda.
Yeah.
So is there any difference between choosing different integer basis for the kernel, or is it all equivalent, the Poisson structure you get?
The Poisson structure sort of is the same, but you can have different actions that sort of complement, that sort of fix failure of log symplecticity. I don't think it matters which one you use.
But then
It
also,
only-
does it matter if you pick a torus of bigger dimension than the co-rank, or does it just not give you anything?
So if you pick that, then, so for instance, if you could choose the torus to be C star to the n, so the maximal
that's
possible, then you would be only considering log canonical deformations, which are trivial. So in that case, sort of the problem is easy.
Yeah.
But also in representation theory, sometimes you have a situation when the torus is big, but only small part of it acts non-trivially. So it has the action has big kernel. So that's also possible.
But then it doesn't matter. You can quotient by the
Yeah.
kernel.
You can quotient, yeah.
So you could raise the same problem for log canonical brackets on a toric variety.
Yeah.
Do these methods extend to classifying deformations on toric varieties?
We hope they do. So that's done when for the case when torus is trivial. So we've done actually for any non-necessarily toric, any global variety, but we don't know how to extend with the presence of torus action yet. But the hope is that it should be true. And then in that case, Poisson cohomology also encodes deformation of the complex structure. So you would need to deform also the complex structure of the toric variety. How many minutes I have left?
You have 10 minutes.
Okay. Any other questions?
Is it at all, it's not obvious to me how the properties of the graph will affect how you can prove this theorem.
Oh yeah. Okay. So maybe a few words about the proof, how it's proven. So as I said, this statement as I wrote here is actually has an elementary proof. So find the weights of the big torus, so the n-dimensional torus, contributing to HP3 where obstruction live. So just as I stated this lemma about HP2, there is some similar statement about HP3. And then the properties of the torus are used to prove combinatorial statement that the positive cone spent by weights in HP2 doesn't intersect, maybe positive cone, so without zero, does not intersect these weights. So this is empty set. So when you expand this power series, the weights in question will always sort of lie here. And so you're using graph geometry to sort of didn't really explain in details, but you use the graph geometry to show that you never encounter this weight. So abstraction always vanishes in your construction.
So is it like iterated Poisson or extension in this case?
It is not necessarily, but like there are some sufficient conditions when it is. The sufficient condition probably would be like when the weights are zero away from this, to the left of this -1 and to the right of this one -1. So that doesn't have to be the case. So if the weight sort of starts with -1, then some negative numbers and ends with -1, then we can prove that it's iterative or extension.
But I don't understand. So the ordering of the indices, what role does it play? I mean,
Well,
you have a
okay.
graph, yeah, so
Yeah.
you can probably just order them so that it's increasing along the graph.
Well, not always. Sometimes you can, sometimes you cannot, because there could be like edge here and then some this non-negative integers will appear outside. And when there are many weights, you may not be able to find ordering that works.
Okay.
So you mean you have to do that ordering, the same kind of ordering for all the weights?
Yeah, and sometimes it's
Yeah.
possible, sometimes it's not. So one prominent example when it is possible in this iterative order extensions here is that case of Bott-Samuelson varieties. So let me briefly say about those. That we have applications of the statement Bott-Samuelson varieties, which certain varieties that appear in geometry of Lie group, flag variety. So I'm gonna use the notations from the previous talk and also very standard notations. So this is gonna be, okay, for me it's complex group, so semi-simple. Semi-simple Lie group. Over C. Then this is Cartan. That's Borel. Then this is Weil group and so on. Then if I take element of Weil group, then I can form there is also flag variety, and I can form Schubert cell in this flag variety. So take closure, so that one is it's called Schubert variety. So it's singular, but its singularities, there is some important information about geometry representation theory of G. And where Bott-Samuelson variety comes in is that it is a natural resolution of singularities of this Schubert, denoted by XU, sorry, XW. So to construct Bott-Samuelson, I need to decompose the word in the Weil group into a product of simple reflections. mean reflections about simple root in the algebra, Lee algebra. But Samuelson varieties define the certain quotient.
It depends on this decomposition, yes?
Yes, it does depend on the decomposition.
Which doesn't have to be reduced, this decomposition.
Doesn't have to be reduced. Yeah. With closures here. So that's called Burke-Samuelson variety. And if it is if the decomposition is reduced, then this is actually a resolution of singularities of the Schubert variety.
The map is given by multiplication.
Exactly, yeah. The map, yeah, exactly, just given by multiplying.
And this is like an iterated TP1 bundle.
That's right. So it's smooth, and it's P1 bundle over P1 over P1 and so on. But so you don't have to assume this condition to study this variety. It's kind of even without this condition, but when it is reduced, it's literally resolution of singularities. So Liu has done some work in maybe 10 years ago. She's done some work with her student on the Poisson brackets on this Bot-Samuelson varieties. So when you start with the group G, it has multiplicative, standard multiplicative Poisson bracket. And that Poisson bracket sort of passes on to all these spaces that I wrote here. So it defines for you a Poisson structure flag variety on Schubert variety. Schubert variety is Poisson submanifold, just a union of symplectic leaves. And but Samuelson variety also inherits Poisson structure, and this map is Poisson. So everything is Poisson here. And what you did with the Alec, they calculated standard Poisson bracket. On this Bot-Samuelson varieties. So they chose the coordinates appropriately. So you have to consider it carefully, and then they calculated the bracket, and the expression they obtained was of this form. So there is some, the way they obtained the formula, there was some log-canonical term, which was sort of easy to calculate. The easy formula for this lambdas terms of these roots above. And this formula takes a lot of room to describe. Maybe half a page to write it down carefully. So I'm just gonna call it complicated tail terms.
Tell us something about.
Well, I'm gonna tell you better way to think about them using my theorem. So these terms, yeah, there is some complicated description of them, but the now we can think of them, I think, a little bit better using the following theorem. We check that the graph for this log-canonical part has no cycles. We can apply the theorem, and the deformation involving all edges in the graph so the graph takes the first order deformation that involves all non-zero weights that are there. Oh, maybe equivalently, maybe some all non-zero weights, recovers this bracket uniquely, so up to isomorphism. The claim is that you start with these terms, which are sort of easy to compute, and then you deform it as much as you possibly can using all of the Poisson cohomology, except you disregard the zero weight one. And then that deformation defines for you uniquely some Poisson bracket. That Poisson bracket happens to be exactly this.
And so why is it clear that it descends to the Schubert variety, to a like regular bracket?
Say it again.
So you say that it descends to Schubert variety. This is a bracket on the resolution,
Yeah.
but why does it?
I guess I think maybe yeah. I think the fibers are connected. So if the fibers are connected, then any Poisson bracket descends. Because and push forward the structure shift is structure shift. So descending is usually the easy part. The hard part is when you lift Poisson bracket to resolution to check that it doesn't have any.
This is the normal varieties, yes, and
Maybe it doesn't really matter that might be the normal. Just the matter is that local functions on here are the same as local functions on here. Because normal. Yeah, you need normality. Yes, sorry, you need normality. Yes.
By standard Poisson structure, you mean our matrix or?
Just I don't know, Semenov Chancharsky, that one, the standard R matrix. Okay.
Very much. Since we are running slightly late, I suggest that the questions can be at the coffee, and we resume at 1:15. Please be on time because we are traveling, so I and then have lunch and have more discussion.